the session now. Okay, our first speaker is Sayantan Chaudhary, and he is going to talk about thermalization phenomena in quenched quantum Brownian motion in digital space. Okay, before starting, to my understanding, this is just a 20 minutes talk. So you can roughly can talk 15 minutes, and we will have a 5-minute discussion. Okay.
Sure. Sure.
Good. Please. Yes.
Yeah. Thank you for inviting me to give this seminar and selecting this work to present in this platform. So I'm going to talk about thermalization phenomena in quenched quantum Brownian motion in de Sitter space. So immediately one can ask for crucial questions: what is quantum Brownian motion and how to perform quantum Brownian motion in our universe, and what is quantum quench and how this become useful for our universe, and why we at all need to thermalize a quantum system, and how exactly this can be done for our universe, and how quench triggers thermalization for our universe. So we have actually done a very recent work with which is there in archive. It is pointed here, and this is I have done with my master's thesis student Shatoki and few of my other collaborators from Germany as well as India. So we have tried to answer this question in detail in this work. So we know that quantum field theory deals with various tools and techniques, and like quantum dissipation, path integral, Brownian motion, random matrices, effective field theory, and many more tools and techniques we use to apply in various contexts. In this work, I'm going to use quantum dissipation, path integral techniques, quantum Brownian motion, out of equilibrium stuffs, and quench. Now, the outline of my talk is basically divided into this subcategories. What is like, I will start with the general introduction, then I will talk about a very good old description of quantum Brownian motion model, which is described by Caldera-Leggett. And then I will try to generalize this idea for quantum field theory in curved space-time, particularly in de Sitter space. Then I will discuss about quantum quench in certain limit in de Sitter space. I will talk about, once the talk is proceeded, I will mention that what do you mean by certain limit. Then I will mention what is subsystem thermalization and why this is needed. And then I will finish my talk with giving some insight to two-point correlation functions with and without having some squeezing in the quantum states. I will discuss the numerical results with some concluding remarks. So let's start with the introduction. The study of Brownian motion of a particle coupled to a thermal bath has assumed great significance owing to its relevance as a robust model of open quantum system in the context of microscopic properties of a particle in general environment. This has been used to study quantum dissipation and quantum decoherence problem due to the system's interaction with the environment. And this model of quantum Brownian motion has proven to be very, very useful idea, not only studies for quantum open systems, but also in different contexts like quantum cosmology, quantum studying quantum correlation problems from different quantum systems, including ADS-CFT. This is very recent progress where people try to use this idea in the context of gravity, gauge gravity duality context as well. So this idea was technically first proposed by Feynman and Vernon very long time ago. And the contribution of the environment degrees of freedom is quantified by the influence functional technique. They call it influence functional technique to calculate the path integrals. And one obtains the reduced subsystem information of interest, which whose dynamics is very important in this present context. And later, this idea was generalized by Caldera and Leggett in their later works. Quantum quench. second idea, because first one is the quantum Brownian motion, second is the quantum quench, which we have also used. So quantum quench is one such technique where the process of thermalization can be realized in the system in the post-quench phase. And this is very, very useful to trigger the thermalization process. It will be clear once I will proceed with the material. And in quantum quench, some parameter of the Hamiltonian change over a finite duration of time, and the initial wave function in the pre-quench process evolves to a state after the quench that is not stationary. One example I have given with a spin system with the nearest neighboring interaction. You can see it's by sigma ix and sigma I plus 1x, and the coupling strength is J. And here you see that I have added one additional parameter, which is time dependent, which is a coupling. Once it is switched on, this has some value G naught, and if you turn switch off gradually, you will see that it goes to 0 or maybe some other value G1 due to having some particular properties or profile in this coupling GT. So this kind of thing we will going to, this is one of the example of a spin system, but for our system, we will use this kind of stuff. So I am giving one of the examples. So these two profiles are possible. One is basically a slowly varying profile. Another one is a sharp profile, sharp change. And here the basic idea is if you have pre-quench state, once you apply this, either this slowly varying change or this sharp change, you can generalize, you can actually generate classes of quantum states which is responsible for thermalization. So these classes are called Calabrese-Cardy state, generalized Calabrese-Cardy state, and so on. Ground state is basically, I'm not talking about, but like from this CC and GCC, one can actually thermalize the system. And this is actual goal, that how to trigger the process of thermalization using this quench. Now, due to this growing interest of study thermalization of integrable systems, there has been huge progress in this direction. There are lots of experimental studies also in the context of cold atoms and free, where the post-quench phase can be described in terms of free scalars and fermions. And this can, as I have told, that there is a common interest in the context of cosmology. So to study the phase transition, and all people have used this kind of idea as well. Now, this is the overall setup. So if you have a quantum system, if you give you a response, it immediately goes to out of equilibrium. Now you can study these correlations and its properties with a lot of techniques presently people use, which is called out of time order correlation functions, chaos, etc. But we didn't do this thing in this paper. But like, if you have this kind of information, if you wait for very long time and don't apply any quench, you will see that the possibilities system thermalizes. But to do that in real life problem, it's not very easy to do that. So if you use the quench, it actually shorten the equilibration time scale, and it actually confirms that at the end of the day, whatever system you have, that actually thermalizes. So quench actually is kind of a confirmation which basically triggers the thermalization process. So this is the Caldera-Leggett model that I was talking about. It's basically described by the three parts of the Hamiltonian. This is called total Hamiltonian. Second one is basically the system Hamiltonian. And this is sometimes called bath or environment Hamiltonian, which is
Excuse me, Sayantan? Sayantan, just a minute. The connection is now not so good. Can you hear me? Is there anyone who can help me for this technical issue? Okay, everybody, just a minute. 지금 이게 튕겨 나간 것 같은데요.
Yeah, I think it was due to the poor internet connection from his side.
Okay.
Probably we have to wait until he rejoins. Let's see.
Okay, I got a message. The speaker will join soon.
Great.
Hello, can you able to hear me again? Sorry for
okay,
the
good.
interruption.
Oh, welcome back. Okay.
Yeah, like all these things happen due to having bad internet connections and all. I'm very sorry for that.
No problem.
Yeah,
So,
sorry. I was here. I can remember. So
yeah,
this slide I have explained.
Yeah,
I think I have told.
So let me just a minute. So you now have 10 minutes. So you understand the time limit, right? So please try to.
Yes, I know that.
Yes.
Yes.
Please, yes.
Yes. So this is the Brownian motion model that we have used, which is the quantum field theoretic generalization of the Caldera-Leggett model, where we can see that there's a free theory of scalar field phi. This is a free theory of scalar field chi, and they are interacting through this interaction term. And this is basically minimally coupled with a gravitational background. And for our purpose, we have chosen this gravitational background to be a de Sitter space. And this metric we have written in a conformal form with having this scale factor and with the square root of this determinant. Now, to write down, the main goal is we treat in this quantum Brownian motion problem phi to be the noise field and chi to be the signal field. And you want at the end of the day to construct an effective field theory of the signal field or chi. So for that reason, you can actually write down an effective potential in the minima of the field phi, and which will look like this. And you will see that before doing this minimization, you will see that the mass terms are basically constant. Now it's basically a space-time dependent quantity, and it is basically given by this n chi square minus this, because this contribution from the interaction will come up here. Now, if you do the path integration in the Euclidean language, then you can actually calculate the partition function as well as the effective action. And you will see that at very long time limit, this interaction part of the kernel will vanish due to having this kind of specific form. It will decay very fast. But the effective potential which contains the coupling, time-dependent or space-dependent coupling, that will be there. That is very good, important information. So if you write down this action in a de Sitter space, then it will be like that. This is the profile we have chosen particularly for this kind of mass, which is a sudden profile. Now, if we do a little bit of algebra and write down this action in a Fourier space and calculate the equation of motion before quench and after quench, you can actually express everything in terms of this expression. And you can actually calculate the solutions, which we call it asymptotic solutions, before quench and after quench, for different initial conditions. Okay, now the point is how this before quench and after quench solutions are connected. They can be connected through Bogoliubov transformation, but these alpha betas are the Bogoliubov coefficient which you can calculate from these solutions. And this ratio of this Bogoliubov coefficients are very important quantity, because that will actually helps you to construct the states on which we are interested in after quench. So pre-quench state is basically the initial state like that. And for the post-quench state, you can actually see, you can actually write down the state from this expansion, which is defined in this box. So depending on the sign, you can call it a Dirichlet state or a Newman state. And for the thermal state, the definition is usual. And a little bit more, like if you have a squeezing, then the definition of this ratio, this beta by alpha, will be a little bit changed, but the construction will be exactly same. It will not be different. One thing it is important to note that these W's I'm talking about, these expansion coefficients, these are basically called the conserved charges for W infinity algebra. And that is playing a very important role to connect with conformal field theory. Now, the subsystem thermalization. So I have told you, once I have a post-quench state, and if I calculate this quantity and if I wait for a very long time, we will see that the system will gives you a generalized Gibbs ensemble. And this is true for both Dirichlet and Newman state. Now one can ask me that how we are actually claiming that this is true, because we can actually see that for post-quench state, and for the thermal state, the number operators actually giving you the exact same contribution, and for which this reason the W charges, the expectation value of the W charges will be same. Now, finally, this is the 2-point functions. We can, since we know the state, so we can actually calculate the 2-point functions for different contributions like ground state, the post-quench states, and the thermalized states. The expressions are very complicated, but I'm going to explain with a plot, then you can able to understand. So this is the expression for the 2-point function for the thermal state. So these are the plots. So this is for pre-quench. We have plotted the chi-chi correlation, del I-chi correlations, and pi-pi correlation. Pi-pi means the momenta for the pre-quench and post-quench states. One important thing I have to mention here, this for chi-chi correlation for pre-quench and post-quench, both we have plotted in a Fourier space, and we have seen for a particular value of the momenta, it is exactly conforms with our observation from Planck 2018 data. And this is like one of the verification that whatever we are doing in a correct direction or not. But we don't have till now information regarding this kind of correlators from the observation, but these are from theoretical intuitions from the model. And for the high temperature and low temperature, you can do the similar kind of stuff for the thermal states. These plus and minus signs are basically the two different parts of the Green's function, having the e to the power minus ik dot x and e to the power plus ik dot x coefficient in the Fourier space. So this is the result. We can see that thermal power spectrum shows like significant features. Till now, this kind of features didn't confirm from any kind of calculation in gravitational space-time. People do that in 1+1 dimension, but this is the first work we did in 3+1 dimension. Now the concluding remarks. So we have provided in this analysis the quantum field theoretic generalized version of the Caldera-Leggett, which describes in the quantum Brownian motion in de Sitter space. We have constructed the effective action by integrating out the noise field and implement the tool of quantum quench in presence of conformal time-dependent coupling or effective mass protocol. We have chosen certain quench profile or theta function for this calculation. Particularly, quench is useful to construct the pre-quench, post-quench, we call it the generalized Calabrese-Cardy state, and finally helps us to thermalize the system in de Sitter space. We have studied the effect of quench with and without having squeezing that I have pointed, how things are going to be different. And we have computed the 2-point quantum correlations with and without having squeezing, also computed 2-point correlators after achieving thermalization. And finally, we have numerically estimated and studied the features. And thank you.
Okay, thank you for the speakers for his interesting talk. Okay, so is there any question or comment? I have a few questions. I'm just wondering, what is your motivation to study this in digital space?
What?
What is your motivation to study this in digital space?
Digital space, mainly we want to do that because we want to directly verify our result in cosmology. Okay.
Okay.
Because in cosmology, particularly, people don't know how to thermalize a very early universe systems. People talk about inflation, people talk about reheating, lot of phases of the universe, but people really don't know, and there is no quantum field theoretic structure yet, which actually tells you that how to thermalize a de Sitter space-time, a quantum system in a de Sitter space-time. And that was the first motivation to do that. Second motivation is before that, whatever studied have been done, it was mainly done in 1+1 because they usually try to connect with CFTs. We didn't talk about too much about CFTs, but we have given a little bit glimpse about that using this W infinity algebra. But this is, you can say, one of the generalization of 1+1 dimensional flat space-time quantum field theory work in basically 1+3 dimensions. So that was the two prime motivation of doing this kind of work.
Mm-hmm. Okay, thank you. So is there any other question? If not, I have a very short final question. So you want to study the thermalization in a Brownian motion. So what would be the signature of the thermalization in your calculation? For example, in 2-point function, what should I see? What would be the physical observable to understand thermalization?
So 2-point function, so if you just compare the before thermalization 2-point correlation function and the after thermalization correlation function, then you can able to see the features, because these are basically before thermalization. Okay. And this is before quench and this is after quench. And once we thermalize, we can see some kind of spectrum in the Fourier space. And the features are very significant in various. So if you ask me that how you can verify that, I don't have correct answer to this question, because till now in observations or any cosmological studies, people haven't talked about thermalization. So first of all, this is completely a theoretical simulation we did. But I have to say that if you ask me that how to thermalize, that we have actually confirmed through the calculation that the system thermalizes, because we have seen that the number operators before thermalization and after thermalization, if you consider that, we see that the density matrix, if you calculate some expectation value of some operator in a thermal state after thermalization and before thermalization with some post-quench state, then if you wait for longer time, we'll see that that post-quench state exactly goes to this thermalized state. So that was the confirmation that whether our system really thermalizes or not. Okay.
Yeah, thank you, Sayantan. So because of the time limit, I think we should move. Let's thank Sayantan again. Thank you very much.
Thank you very much.
Okay, so could you please next speaker please share? Oh, yes.
Yeah. Let me share my screen.
Yes.
Okay.
Okay, so our next speaker is the Dr. Kazem Bitasser Fadafan, and he's going to talk about the magnetically induced holographic composite inflation. Okay, thank you.
Okay, very good. My name is Kazem Bitasser Fadafan. That was right. First of all, I would like to thank the organizer for giving me this opportunity to give a talk here. My talk is based on this work. You can find more details here. It has been done by Amjad Ashurian and Muslim Ahmadvan from Tehran. I start with the motivation. One of the well-motivated scenarios which may describe the inflation is strongly coupled actually gauge theories in which the inflaton field emerges as a bounded state breaking a chiral symmetry at some energy scale. It looks like some QCD-like theory. In fact, in this effective theory, above this scale, there is no such a bounded state, and instability of the inflaton mass due to radiative corrections can be circumvented here. Actually, in this talk, we investigate a strongly coupled gauge theory for inflation, introducing which the chiral symmetry breaking occurs due to a background magnetic field. This is the main assumption here. In such series, we cannot use conventional perturbative methods, and we need some non-perturbative tools. And one of the approaches through which many features of a strongly coupled system can be studied is ADS-CFT correspondence. ADS is here is a ADS space-time with negative cosmological constant, and CFT is a conformal field theory, which is known also as holography or gauge string duality. We employ this tool. The model that we are going to use is a top-down model based on the D3 D7 brane system. And the framework is ADS QCD. We replace QCD here because we are going to have field theory which looks like more to QCD. Actually, it's not exactly QCD. Now I explain the geometry. We have a stock of D3 branes. Here you see 10 dimension of space-time. D3 runs over time, x1 and x2 and x3 directions, and you embed a D7 brane in this background. Then we have a D3 branes, and we embed D7 branes here. Here L and omega are perpendicular to both D3 and D7. Then you have some strings between D3 and D7s, and this is given by L, the distance between these two. And when they are changing, you are studying the mass of the quark. Then the quark mass and the boundary theory is changing by changing this L. The geometry is given by this metric, and the overall factor here is the GUV, is the asymptotic value of the gauge coupling. And also the space, the forest space-time is given here, and the extra dimensions appear here. Two perpendicular dimensions, L and omega, are explicitly written here, but we chose omega to be 0, then we work only with L. Also a small r is related to rho squared plus this L squared, which is the radial coordinate, and this is correspondent to the energy scale in the gauge theory. And the big R is given by this equation. It's given by GUV, NC is the number of colors, and alpha pram is proportional to LS squared, which is the string tension, and LS is the string length. And we choose GTT to be -1, Gij equals to AT power 2 delta Ij, and AT is the scale factor. Then we know the gravity, and we should use the ADCFT. And the main quantity that we are going to study is this big L. Okay, the condensation which breaks the correlate symmetry of the theory is entered by studying the embedding function L. And according to the Dirac-Born field action of the D membrane, the action of for this L is given by this. And as I have mentioned, we have a stock of D3 branes, and we embed the D membrane, and we should study the action for this D membrane. Then this T7 is the tension of D7, and L also appears under the square root. L prime and L dot are derivative respects to rho and time. And running of the gauge coupling can be parameterized as e power phi equals to GUV squared beta, which equals to the Yang-Mills coupling here. And beta R is related to the background magnetic field B with this equation. Then it's clear that when B is changing, this e power phi is also changing as well this G Yang-Mills. This is the main assumption here, that we use this background field to break the chiral symmetry. Okay, we should solve this, the equation of motion which comes from this action. Certainly we should do this numerically to find the solution for L. Here you see that in the vertical line L, and in this direction we see rho, which somehow shows the energy scale in the theory, and this is the UV somehow at 20. And in this way, we are increasing the time. At the early times, we have a flat embedding, but at the late times, suddenly peak appear here, and we see some interesting behavior. We use the iterative approach to solve the equation of motion to find this L. And UV asymptotic embedding solution is corresponded to this equation, L equals to M plus C over rho squared, where M is proportional to quark-like mass by this equation, and CT is associated to the condensation QQ bar, CT over 2 pi alpha prime cubed. Here you see the plot of CT versus time, and it is clearly seen that after a while we have oscillation behavior around the true vacuums, which is very interesting, and we should study other parameters in the theory to see if it works for inflation or not. Okay, the next step, we study the Hubble parameter to answer this question. But we have to fix the number of color here to be 10 power 7, and we introduce the tooth coupling, which is G squared UV times number of colors. We chose to be this number. Also, another parameter in the theory is coming from the Planck mass, which we scale quantities with this. And NP equals to this number. We plot Hubble constant, and we see that it's constant, and we see exactly this oscillating behavior as we see that decreasing oscillatory behavior at the late times clearly after inflation ends. And you see that from 19 to 105, this oscillation happens. Okay. Now, because the system is time dependent, we go to the slow roll inflation conditions. The first slow roll parameter quantifying whether inflation takes place at a given time is given by epsilon, which is given by this equation versus the Hubble parameter. To maintain inflation for sufficient amount of time, the second condition, which should be less than 1 during this period, is given by eta. And you see that the Hubble parameter in the denominator has been scaled by Planck mass, and P appears here. And Another condition, the amount of inflation can be quantified in terms of the number of e-folds, and it can be integrated from the CMB time to end of inflation by this relation. Okay. Now we asked to study the observable parameters in the theory, but should introduce first them. The dimensionless power spectrum of the scalar fluctuations is defined as this. Epsilon appears here in the denominator. Another parameter is deviation of scalar power spectrum from scale invariance, which can be parameterized in terms of scalar spectral index, which is defined in terms of slow roll parameters as this equation, which is related to eta and epsilon. Another important parameter is the tensor to scalar ratio, which is indeed a measure of magnitude of the tensor power spectrum, or equals to delta t squared over delta s squared. Okay, we can obtain this ratio at the CMB time from the first slow roll parameters, and then one gets that R is proportional to 16 times epsilon, and the current upper limit on R is R less than 0.056. Okay, now we go to the parameter space or the model, and for 3 different values of NP and fixing the number of color to be 10 power 7 and 60 e-folds, we check that how the parameter space meets the Planck data. Here the green line shows the Planck results, and delta S squared versus the tooth coupling parameter in the theory shown in these 3 plots. Red, blue, and black ones belongs to different values for NP. And when there is a crossing point, for example, for black one here, you see that for this value of lambda, it happens. But for blue lines, the lambda should be this one. Then we can find that in which parameter space of the theory we meet the Planck data. Also for an S, the validity region is here versus lambda. And for small r, we see that all 3 curves here are larger than 0.07 and less than the larger value that I show you in the previous slide for small r. Okay, the interesting question here is that about Lie's bound, because you are going to see that for the obtained are larger than the 0.01 of the model, one would expect a large field model of inflation. Then we should answer this question in our model, if this bound is satisfied or not. One should note that the condensation is mass dimension cubed composite scalar field. QQ bar is given by this R cubed C over 2 pi alpha prime cubed. And in order to transform it to a canonically normalized mass dimension 1 scalar field, it should be divided by a mass dimension squared parameter in this way. But in the denominator, you see cutoff, this is cutoff of the theory. On the other hand, the UV cutoff of the theory should be greater than the symmetry breaking scale by this condition. Then in Planck units where R equals NP and hence Ls is proportional to 10 power 4, delta phi is less than 10 power minus 3. This is very small. Therefore, despite predicting that R larger than 0.01, the excursions of the canonical field remains below of the Planck mass. That's interesting because now if you are going to think about higher dimensional operators that should be added to the theory, you can claim that these are so small. Okay, I'll go to the conclusions. We showed that the magnetically induced symmetry breaking case can also cause a long enough inflationary period, which incidentally produces signatures compatible with the latest Planck results. We consistently solved for the 4-dimensional spacetime and found the embedding function of the dismembering through an iterative method. This allowed us to see both inflationary epoch and the ensuring rating phase, in which the condensate oscillating phase in a unified picture happens actually. We found sets of parameters for the microscopical parameters of the model that are observables, including amplitude of density perturbation, the scalar spectral index, and the tensor to scalar ratio are all in agreement with Planck bounds. And the interesting result, although the model reproduces a large amount of tensor to scalar ratio in violation of the Lie's bound, the canonical mass dimension 1 scalar field displacement remains below the Planck bounds. Okay, it will be interesting to study the model further, particularly in connection to the mechanism for rating after the inflation. As you see in this picture, this is a Persian carpet. It is not complete. It needs more work to be done. And when you are using ADS-CFT, this is not all the story. We should work more to exactly do the problem and solve it. Okay, thanks for your attention.
Okay, so let's thank Kazem for his interesting talk. Is there any question or comment?
I have questions.
Sure. Yeah, please.
Yeah. First of all, like once you talk about this DBI action,
Right.
if we go back to the long story, like David Tong and Eva Silverstein and those people, once people have proposed DBI in the sky, there is a paper very long time ago. Like here, I just one thing I didn't understand. You have included this L. Suppose I treat that L to be your field. This field is function of space and time both. And I didn't understand that, because like once you do cosmology, like particularly the metric, whatever you have chosen, is it like your field?
I missed your last part of the question.
Like you have a field and you do the
Sorry.
part of
Takahiro, can you hear me?
Yeah, I can hear you, but I can't hear you, the voice of the person that is asking the question. I think I got the point.
Okay, so Sayantan, you are talking now. So can you write your question in the chatting window?
The field as well as the metric, and you talk.
Okay, just to save a time, I can see the Takahiro is raising his hand. So could you do first, Takahiro?
Yes. So you introduced ADS-CFT first, but at some point you talked about inflation, which is usually to zeta. So I'm confused. What is the relation between ADS-CFT and inflation? Is it directly related?
Good question. Actually, we first assumed that there is a strongly coupled gauge theory. This is the main assumption. Then the inflaton is a bound state. Yes, is that clear? But if we accept, if we accept this idea, then we say that okay, you're studying this gauge theory, it is not possible by perturbative. Then we go to the non-perturbative tools. Then the ADS-CFT plays a role. And we use ADS-CFT to study this strongly coupled system. This is the main point.
So using ideas of ADS-CFT, and you consider really Rosetta like inflation universe. Is that correct?
Yeah. First, we say that the inflaton is a bounded state, which is coming from Carlet symmetry breaking of this strongly coupled. And then we model this strongly coupled by a D3D7 system and use ADS-CFT dictionary to relate the results to the disinflation, slow roll inflation parameters.
I see. Thank you.
Okay,
Thanks for
so
your
Yes, I was disconnected suddenly.
yeah,
Yeah.
That's
So
fine.
yeah. Okay, so Sayantan, could you, I mean, repeat your question in a very short sentence?
yeah, so that's my point. Is your field is breaking the homogeneity and isotropy from the starting point? Is it
No, no,
so?
no, no, no. This is the space-time metric. Yeah, as you see, this is
Yes.
the GTT is -1, and this GIJ is 80 powered.
Okay, that's true. Then why your L field? If you call it, if I call it L as a field, why that this is function of rho and tau both?
Good question. Because we are working in the extra dimensions, and we use ADS-CFT to reinterpret the extra dimensions. That's the main point.
Okay.
You see
And
the definition of L is here.
yes.
I put
And
my emails in the first slide. I'm happy to send email to talk more about the.
Okay, thank you,
Yeah.
Kazem and Sayantan. Unfortunately, because of time limit, we should
Yeah.
close the talk. But I think you can discuss after this talk. Okay, thank you very much for your interesting question. Okay, good. So let's continue to the third speaker. Francesco, are you here? Yeah.
Yeah.
Okay. Could you share your slides now?
Yeah. Let's see. Okay. Do you see the slides?
Yeah, very good. And I think you can. Are you ready now?
Yeah.
Okay, good. Very good. So, okay. So our third speaker is Dr. Francesco Serra, and he's going to talk about an effective two-body approach to the hierarchical three-body problem in GR. Okay, thank you.
Thank you for having me. And well, yeah, I'm going to tell you about this quite ancient problem of the three-body problem in gravity, but also about how we can study this problem with more modern ideas from the effective field theories. And so as the title suggests, I'm not going to talk about a generic three-body problem because it would be quite chaotic, but I'm going to focus on the hierarchical three-body problem, which is a special case in which one of the three bodies, let's say the third, is very distant from the other two. And so we have a hierarchy between the typical separation of the third body from the other two and the typical separation of the other two bodies between themselves. And this hierarchy allows us to set up a perturbation theory because we can build a dimensionless parameter, this ratio of the typical separation length scales, which will be much smaller than 1. And basically what happens is that the third body acts as a perturbation on the other two bodies, which form a binary system which is only slightly perturbed. And this perturbation will be bounded by the size of this small coefficient, small dimensionless parameter. So what we will have is that there will be two orbits, the inner orbit of the tight binary system, and then the outer orbit of the third body that orbits around it. So it's well, these kind of systems are ubiquitous in the universe. We have some of them above our heads hovering. These are the satellites that orbit around the Earth, that are indeed affected by the presence of the moon. So in such a way that they can even crash into the atmosphere if they are launched in the wrong orbit. Then leaving the solar system, we can find other such systems in exoplanets that orbit close to their star, but which often are observed to have an orbit in the opposite direction to the spinning motion of the star. And this is quite unnatural unless there is some mechanism that flips the orbit of the planet in such a way to make it retrograde. And this can be achieved if there is a third body perturbing the orbit of this exoplanet. And then, leaving the galaxy, we can find another example in compact binaries, which could get to merge much faster if there is a third body orbiting not so close but not so far. So all of these systems have in common that the small perturbation of the third body must in order to give a sizable effect, needs to pile up on many orbital periods. And this leads us to consider the secular dynamics, which is the dynamics of these systems on timescales much larger than the orbital period of both the inner orbit and the outer orbit. And this secular dynamics has been studied for centuries. And there have been a few surprising findings. First, the Kozai-Lidov effect, which is basically an oscillation of the eccentricity and of the inclination of the inner binary, which is caused over these very long time scales by the presence of the third body. Then more recently, it was found that higher orders in this perturbation theory can even cause orbital flips, which is what we were looking for to explain the retrograde exoplanets. So this is quite interesting. And also some recent works have touched upon the study of the effects of nonlinearities and relativistic corrections, which are found to contribute to these effects in a way that is not super clear, because these all of these contributions compete with each other in order to either enhance the oscillations and the excursions in the eccentricity, or in order to prevent these changes in eccentricity and in inclination. So what is not clear is which is the hierarchy between these contributions. And so the state of art of this study of the secular dynamics is that we do not have a complete understanding of these dynamics. So what is interesting is to consider whether effective field theory could help in gaining a more systematic understanding of these secular dynamics. And this is what I've done with my collaborators. So it is well known that effective field theory is a very powerful tool to describe systems in which there is a well-defined separation of scales, and this is perfectly the case of our hierarchical tripods, because as we have seen, the size of the inner binary is much smaller than the size of the outer orbit, and the same is true for the periods. And so we have on the UV side of the effective field theory, the inner binary, which is microscopic, which is fast. I mean, it has fast modes. And then going to larger scales and longer time scales, we find the outer orbit and eventually also the time scales of the secular dynamics. And the idea of effective field theory is basically to single out the UV degrees of freedom, and then in the Wilsonian picture to integrate them out in order to obtain an effective action which depends only on the IR degrees of freedom. And this has been done in the context of general relativity for the last 15 years, but focusing on the study of binary systems. So what we want to do is to follow these footsteps, but considering a slightly more complex system made of 3 bodies. And well, let me anticipate the result, which is that once we integrate out the short scale modes that encode the dynamics, the details of the inner binary, we get to an effective theory that couples the third body to an effective point particle, which represents the inner binary. And so it will have some multiple moments, it will have a mass, an angular spin, and a quadruple moment, and so on. And we want, before getting to the secular dynamics, we want to understand, to compute these multiple moments. So in order to do that, we have to start from the UV theory. And this UV theory, in the simplest case, will be the theory of general relativity with 3 word lines, the word lines of our 3 bodies that are coupled minimally to gravity, which is this expression that I show here. And well, since there is this rich matter content, we cannot hope to solve this exactly. So it's very useful to consider the so-called post-Newtonian approximation, in which we assume that all of the deviations from Newtonian gravity are very small. And in this assumption, we can integrate out the modes of the gravitational field that give rise to the potential that binds the inner binary. And in such a way, we obtain an effective action coupling the 2 bodies to the third body once the gravitational modes of the potential have been integrated out. And here, well, this integration is just done by considering the diagrams of exchange of these graviton modes. And I reported a result of the interaction to the first order in this post-Newtonian approximation, just to show you that it will have some vertices where the gravitons that have not been integrated out are evaluated on the word lines. So in order to arrive to a picture in which we have a particle, a single particle representing the binary with some multiple moments, the most straightforward way is to consider a multiple expansion of these gravitational fields in the interactions. And so if we do that, and then we integrate out the modes of the orbital modes of the inner orbit, that is the dependence of the trajectories of the first and second body on time, integrating out these modes, we obtain finally our effective action for 2 particles. And what we see at the level of monopole is that indeed this effective action has only 2 word lines. The word line of the third body, which was not touched by this integration of short modes, and then a word line that follows the center of mass of the inner binary, and which corresponds to a particle whose mass is the total mass of the inner binary plus the binding energy. So, and this is the monopole, and we could we can compute the same effective action for the dipole term. And what we find is that this particle that represents the binary also has a minimal coupling of that corresponds to the minimal coupling of a spinning particle to gravity. And this is the coupling of a particle with spin corresponding to the angular moment, to the Newtonian angular momentum of the inner binary, which is very intuitive and very nice. And okay, we could think about going to higher orders in the multiple expansions, and indeed we can already guess what is the leading term in the effective action for the quadruple, because we know by symmetry that this will the quadruple moments will have to couple to the components of the Weil tensor. And okay, the computation of these quadruple moments is something that we are doing now. So for today, we will have to be happy with the dipole. But we can actually be happy with the dipole, because what we are interested in at the end of the day is the secular dynamics. And actually in this GR post-Newtonian expansion, the secular dynamics at first order in the post-Newtonian expansion. And we can already compute it by now integrating out the modes as scales shorter than the outer orbit, and at time scales shorter than those of the outer orbits period. And if you do this, which is the same that we did integrating out the degrees of freedom of the inner binary, we find a spin orbit coupling that comes at first order in the post-Newtonian expansion, which is a coupling between the spin of the composite particle that represents the binary and the orbital angular momentum of the outer orbit. And this basically tells us that because of relativistic effects, the spin, the angular momentum of the inner binary undergoes a precession around the angular momentum of the outer orbit. And this is it for today. So I hope I was able to convey that the EFT can indeed provide a systematic description of hierarchical triples. And okay, next will come the quadruple, and I'll let you know about it. In the meanwhile, thank you for your attention.
Okay, thank you. Let's thank Francesco for his interesting talk. Is there any question or comment?
I have a question.
Yes, please.
So, like, could you please go back a little bit of your slides once you have expressed the effective action?
Here?
Before, you have written some path integral.
Sorry?
Before that. Yes.
Okay.
Here you have written the so your main motivation is to construct the effective field theory, that I can understand, where you try to integrate out the UV modes of the theory. Okay. Now the thing is, you have written a Lorentzian path integral. My point is to understand this effective field theory action at the IR, how you have done this path integral in a Lorentzian language, because in the Lorentzian language, finding the saddle points are very difficult.
No, you're absolutely right. This was a naive writing just to symbolize the effective action, but there are all those caveats, of course.
So this is one of the point I just want to make. And second one, once you talk about graviton, could you please go a little bit more?
Sorry.
Yes. Yeah. Here. So you say that there is a background G mu nu tilde plus there is a perturbation, but what is the perturbation parameter? I just want to ask.
Sorry,
what is the perturbation parameter? Because we usually do at G mu nu plus some parameter times graviton, capital H mu nu.
Yeah. Okay. If you want, this is this capital H mu is not normalized canonically. So you could write the same with a standard kinetic term for this H mu, but now it will come in any interaction suppressed by 1 over n Planck. So that's your parameter.
And can you just comment on a little bit about non-linearities, because that is a very interesting issue.
Yeah, so that's something that arises now in these equations that you usually get.
My point is, like, once non-linearities are there, the perturbation theory will break. Okay, now how you tackle or handle that non-linearities in your calculation?
No, indeed. So luckily for me, at this order of computations that I shown today, linearities are still not present, because you are not considering higher orders in perturbation. So you are just considering the first order, and that's I mean the leading order, and that's it. Then when you consider, for instance, higher orders like the octupole order in this multiple expansion, then you find out that there can be competing contributions from nonlinear terms deriving by quadruple squared contributions. So this is something that, yeah, of course, I still don't understand.
But my question is, if there is non-linearity, will the perturbation theory will work?
It will work to some extent. There are some orders. The first leading order in perturbation theory, for instance, is fine. Okay.
Okay. So, sorry, I think that because of time limit, I think we should stop this discussion now, and probably you can discuss later. And I can see the Max has a question, right?
Yeah, well, I wanted to ask a question to the speaker, but you can also proceed. Otherwise,
no, it's okay. It's okay, please.
Yeah. So first of all, Francesco, thank you very much for this talk. I just want to ask, so in order to see if I really understand the philosophy behind this. So usually in this two-body approach, we find this if effective action for the observer at infinity by integrating out those UV modes from this binary system. And now in this case, if we add a third body and we have this separation of scales, as you said, then so is it the case that then basically the integral now contains two kinds of UV modes? So the very high UV modes we integrate out for the inner orbits, and then we also have this to integrate out that region with the kind of middle frequency mode to again find this effective action for an observer at infinity.
Yeah, so it's as you said, but I mean it is you first integrate out the shortest wavelengths that you have, and that you get a first effective field theory, and then you do another integration of these middle range but still short enough wavelengths, and you get the definitive effective field theory that you can use to describe the secular dynamics. I don't know if this was the point of your question. I think.
I just wanted to clarify if I understood this correctly. Yeah. Okay. Thank you.
Thank you.
Okay, so let's thank Francesco again. Now, so final, the last speaker is Max. Can you share your screen?
Yes, I think I have shared. So can you see them?
Just a minute. I cannot see. Francesco. Okay, I will. Okay, good. Okay, good. Now I can see.
So you can see them, okay.
Right.
And you also can see this red cursor, right?
Okay, very good, good. So, good. So our last speaker of this session is Dr. Max Walkentin, and he's going to talk about the Casimir effect in the presence of infrared transparency.
Okay, so hello everybody. So first, thank you very much for, so thanks to the organizers to giving me the opportunity to give this talk. Okay, so my talk is based on my recent work. I put in the archive number here. And okay, let me start by giving you a short summary of what this talk will be about. So probably all of you are familiar with the Casimir effect. So we consider a quantum field in the vacuum in the presence of usually fixed boundary conditions. And so the simplest example would be to just take parallel plates with the Dirichlet boundary conditions, and then in this situation one finds so that the plates, so that there is an attractive force between the plates given by this formula here. So now in my work I wanted to answer the following question: what if we instead that the quantum field obeys those fixed boundary conditions? What if it has localized kinetic terms on the plates? Intuitively, one would then assume that high frequency modes are suppressed on those plates, and the low frequency modes are unaffected by that. This phenomenon, which is sometimes called infrared transparency phenomenon, it was introduced and studied in the DGP model. So already 20 years ago, but however, so in the DGP model, this phenomenon was not investigated in the context of the Casimir effect, but as a way to modify gravity at large distances. So therefore, in my talk, I will briefly review the DGP model and explain this infrared transparency phenomenon, and then I will show you the calculation to find the Casimir force in this model, and then we will see that indeed the plates or the branes act as effective, so momentum dependent boundary conditions, and but so since there's still this DGP behavior, of course, due to this, not all modes are fixed at the boundaries, but some of them leak out, and this leads to the deviation of the Casimir force, which is given by this expression here. So at least in the leading approximation, there are also higher order terms. So and here you see, so the new length scale enters, where RC is just basically the coupling of the localized kinetic terms to the plates. Okay, so now you might naturally ask, why should I care about this result? Okay, there are several possible answers, but let me just point out the following thing. So in the case, usually one considers the electromagnetic field for the Casimir effect, and in that case, it's fairly easy to construct plates with Dirichlet boundary conditions. We just take conducting plates. But in the case of the gravitational field, this is very hard to do so, even in principle, because the gravitational field interacts very weakly with any material, and hence this present mechanism, which I will describe here, is maybe the best chance to actually realize setup where one can have a gravitational Casimir effect. And of course, so if one would be able to observe such an effect, it would be amazing, because this would indicate the existence of gravitons. Okay, let's first discuss the DGP model a little bit. So one of the reasons to introduce the DGP model was to answer the question, why is gravity so weak, and hence offer a solution to the hierarchy problem. And this model, since this DGP model modifies gravity at large distance scales, it was hoped to give an explanation for this cosmic late time acceleration, and maybe even without the need for a cosmological constant. Okay, so and besides those phenomenological reasons, Also, so this model has, from a theoretical viewpoint, has many interesting features. For example, it is a ghost-free, non-perturbative model for massive gravity, where the graviton is actually a resonance. Okay, now let's have a closer look at this model, how it achieves these features. So, so this is the action of the DGP model. So it is a 5-dimensional model with this 5-dimensional Einstein-Hilbert term here. And this is the 5-dimensional and hence fundamental Planck's scale, M star. Now the standard model fields, they are localized on the free brane, which in this model is our universe. So we live on this free brane. And now the crucial ingredient in this model is this localized, this induced 4-dimensional Einstein-Hilbert action with the usual curvature term and the usual, so our observed Planck scale. And this lives on the same brane as the standard model fields. And therefore, one way to think about the origin of this term is that the standard model fields, that they renormalize the graviton propagator on the brane via loop corrections. Okay, so in order to understand this infrared transparency phenomenon, we don't have to consider the full spin-2 theory, because we only care about the particular pole structure of the propagator. So we can simplify our discussion with just considering this toy model, which is thus the massless scalar field with this localized curvature term on the brane. Now we can perform this dimensional reduction by just expanding the 5-dimensional scalar in this way. So we have here these 4-dimensional Kaluza-Klein modes, and they are weighted by these mode functions, and one can solve for them and finds this expression. So then, if we are interested in the potential energy between two static point sources, then we find this potential. And so since we see that for large masses or large frequencies, the so the mode functions are suppressed. And this leads to this behavior that for small distance scales, we get the usual 4-dimensional Newton potential. But for large distance scales, we get the 5-dimensional potential. So the branes are transparent to, or in this case, the one brane is transparent to the infrared modes. Okay, so far everything I said has been already known for a long time, but now let's extend the DGP model by adding a second parallel brane. So now we have two parallel DGP branes, and again I will only work in this simplified scalar field toy model. And at the end, so for people who are interested, I can explain why we expect the same result to hold for the full spin-2 theory. Okay, so to find the Casimir energy, we need to regularize our system. For this, we put it in a box with periodic boundary conditions. The box is of size L. Of course, equivalently, we just put it on a ring with size L. So the branes are displaced by this distance R. And then we do the same Kaluza-Klein decomposition. Now the index alpha enters here, which I will explain on the next slide. Okay, so now, since we now dimensionally reduced the system, we have those Kaluza-Klein modes, which just obey the massive Klein-Gordon equations. And we have these mode functions which obey this Schrödinger type differential equation. And this is subject to appropriate boundary conditions. So in particular, so we have that mode functions are continuous at the branes, the derivatives are discontinuous, and of course they have to be periodic in the size L, the size of the ring. And this periodicity condition then leads to a mass quantization. So the masses are not arbitrary, but they obey this form. So there are solutions of this formula here. And yeah, and so we can divide the mode functions in even and odd ones. So alpha 1 is even, alpha 2 is odd. Okay, okay. So one step back again. So this of course, since it is a transcendental equation, it cannot be solved analytically, but we can get a picture. So we visualize the system by taking two extreme cases first. So we take the case where the masses are much smaller than 1 over RC. So in this case, the masses are just given by this 2 pi n over L, which is just the usual masses for a ring without any boundary condition. So just the ring without branes. So in this regime, the modes don't see the branes. And the opposite regime is the one with very large masses. And then this is so the masses are given like by this, and this is effectively just the case where we have these 2 points on the ring, which have the Dirichlet boundary conditions, and the points are separated by this distance r. So these are these extreme 2 cases, and of course we have the middle transition region, which we can only resolve numerically. Okay, and of course we also, to find a finite Casimir energy, we have to also add a high energy, a high frequency cutoff over 1 over A. And so this is the summary of the length scales involved in this system. And yeah, and at the end of the day, of course, we want to send the high frequency cutoff to infinity and the system size to infinity, because this is the case where we are interested in. Okay, so we now can just quantize this system in the usual way. It's just a 4-dimensional system now, and these masses which we have here, they again obey that mass quantization equation which I showed you before, and the whole information about the branes is now encoded in these solutions of the masses. So yeah, then we have to so for the Casimir energy, in order to have a finite result which is cutoff independent, we have to subtract from this energy the divergent part, which we get by calculating the energy for a system without the branes. So we subtract this one, and then finally this is the Casimir energy which we will get. Okay, so this expression cannot be solved analytically. As I said, first reason is because the masses cannot be solved analytically, and the second thing is that with higher and higher dimensions, this sum here, or the integral, becomes more and more intricate because we have more transverse momenta which we have to integrate over. So therefore, we have to rely on approximate methods and to numerical methods. So I will now show you 2 cases where I found a result for 2 dimensions and 5 dimensions. So this is the result for the two dimensions. So yeah, so I was able to find this functional behavior approximately, so a perturbative expansion for the Casimir force, and these coefficients and the ones which are hidden here, we can find numerically. And okay, so from this result, we can read of 2 observations already. So the first one is that, so indeed, in the leading order, the DGP branes, they act as effective Dirichlet boundary conditions. So this leading order term is exactly the same as we would get for just taking 2 plates in 2 dimensions with Dirichlet boundary conditions. But since we don't have Dirichlet boundary conditions, but localized terms, we have, of course, the situation that some modes will leak out of these branes, and this exactly is what is responsible for this modification of this Casimir force. In the next to leading approximation, we get this term here, which is suppressed by this geometric mean between the distance of the branes and the RC, which is the crossover scale. So therefore, we see, since this is a plus sign and C2 is positive, we have the Casimir force gets weaker than the usual one. So here is the plot. So the blue curve is just what we would have for the Dirichlet case, and the red curve is the one which we get for the GP situation. Okay, and then so the last result for the 5 dimensions. So there I solved the Casimir energy numerically, and so these are these red dots. This is the numerical result, and then we can compare to. So I choose as a functional form. I choose the very analogous one to the situation of 2 dimensions. So again, we have this suppression with this scale, just that we are in higher dimensions now. And we see that the red curve fits very well to the numerical result. And by this, we can fix the C5 coefficient. So therefore, from this, we see that the Casimir force, again, has basically so qualitatively the same form as in the 2-dimensional case. The first term is, again, the standard result for the Dirichlet clay plates in 5 dimensions. And then there's a term which comes from the DGP behavior, and again it weakens the Casimir force because we have a plus sign here. Okay, and just to conclude, so so we saw that indeed the DGP branes act as effective boundary conditions for even the gravitational field. So therefore we can find the Casimir effect for the gravitational Casimir effect, and but since the DGP branes leak some of the modes, we get a deviation from the usual result. So the Casimir force is weaker than in the standard case. And the last point I want to make is that so this result really does not depend on the number of dimensions as we saw. So as long as we take just co-dimension 1 brane, so the branes have just 1 dimension less than the dimension of the full spacetime, we get the same result. So exactly this is what I want to say. Thank you very much.
Okay, so let's thank Max for his interesting talk. Is there any question or comment?
I have a question.
Yeah, sure.
Yes.
Yes. You actually have used a scalar field which you embed. I have seen in the DGP model.
Yes.
There is an extra dimensional term, which is the kinetic energy, and there is a localized term with brane, delta function. Now my question is...
So you mean
yes.
this one?
Yes.
One brane.
So my question is how you ensure that the scalar field is stabilized, because once you put anything in the like extra dimension or in brane, there might be a question regarding the stabilization, because this phi is in principle called the modulus, and that modulus, if it is not stabilized, then how you can ensure that this whatever energy, the Casimir energy, the regularized Casimir energy you are calculating, this is completely correct?
Yes. Okay. So this is a good question. I mean, I now know. So this is a So this is a very basic problem for basically all systems when you take branes. And so in this case, as I understand this whole story, if you treat this modulus field, so this corresponds to the size of the extra the dimension. And if you talk about compactified dimension, so the extra dimension is not infinite, then indeed this modulus field, it corresponds to the size, and then if you don't come up with some effective potential which stabilizes this, then it could happen that for instance, the dimension grows to infinity or collapses and so on. But I'm not sure if this is the problem applies in this DGP scenario where we really take full infinite dimension. So the dimension is infinite, so there's no degree of freedom which lies in the dimension. And this scalar field phi, this is not a modulus field. It is really just some scalar field living on the brane, which is just a fixed orbifold in infinite extra dimensions. So therefore,
my question. That is my question. Once you additionally input something on the setup, immediately this is destabilize the setup. So how you can assure that this stabilization has been maintained? That was
okay.
my question.
Yeah. Okay, but I have to. So you're saying if we have a fixed orbifold, so which is tensionless. The moment we put a scalar field on that, so what exactly is not stabilized in this case?
And my another question is regarding this Kaluza-Klein decomposition. You talk about the lowest mode and higher order modes by summing over n. Just I want to ask that how one can see the effect of this higher Kaluza-Klein states in the Casimir energy expression. Could you please tell us about something about that? Because as far as I know, this is kind of infinite tower of energies. Okay, the decomposition. So,
yes.
and this is discrete. Now I'm saying that how that is going to affect your Casimir energy, how this Kaluza-Klein decomposition is directly related to the final result, how one can see the explicit effects of each and every Kaluza-Klein states there.
Well, so you can see this from this picture here. So what I mean with high energy and low energy modes are the modes which are related to this 1/c here. So the modes which live here. So these are the low energy modes, and these are the high energy modes. Okay. So then, and of course, so this is exactly what gives us the result at the end. Because if you would not have this regime here, so if there were no low energy modes, if all modes would be really captured on those branes, then it would be just the same case as the Dirichlet boundary conditions in the usual electromagnetic case. So the field cannot escape the plates, and then we would have the usual Casimir result. But in this case, we have these low frequency modes which don't see the branes because they're infrared, and therefore they are not captured. And this is what at the end leads to this result. So now I think that maybe your question also means to ask what happens to this very high frequency modes, but this is the same case as for the usual Casimir effect case. So the Casimir effect is an infrared effect. So the high frequency modes don't contribute to that. So in the case of the electromagnetic field, we have the same thing. So the conducting plates, they're obviously not able to really contain all the infinite up frequency modes, because then the plasma frequency is just finite. So therefore the field would leak out as well. But if you calculate the Casimir effect and you calculate this renormalized energy, you really see that this high energy effect does not enter the Casimir effect. And this is the same thing here. So the high frequency modes are cut off by this 1/a, which you can think as just some high energy cutoff in the DGP model. The DGP model has to be an effective field theory, and beyond this frequency, it does not hold anymore. But anyways, we see explicitly that the Casimir effect is not dependent on this thing, because again, it is an infrared effect.
Thank you.
Yeah,
that's so.
So
I just want to say, just regarding your first question, I mean, again, so I did not completely understand why in this case of orbifold infinite dimension, why you would have this type of stabilization. But maybe we can talk about this after that via email or something.
Sure. No problem.
Yeah, sure. Okay. Thanks. Let's thank speaker again. So I would like to thank all speakers in this session and everybody in this session. So because of this time limit, I think I should close this session now. Okay. Thank you very much.
Thank you.